So yesterday we worked on finding inverse functions. Today we're going to kind of build off of that and kind of explore more about what inverse functions are, what they do. So starting off with this kind of quick turn and talk and asking you to complete the tables by evaluating the function and its inverse for the specified value of x. So and this is before our notes, this is just kind of a classroom activity to set it up. If we plug in the value 1 in for f of x here, we would get 1 plus 5 would give us a value of 6. All we're doing is substituting that in. So if I plug in 1 plus 5, I get 6. If I go negative 2 plus 5, I get 3. If I go 6 plus 5, I get 11. Now, if we calculate this new table of values for our inverse function, this x minus 5, this is where we'll plug in our x value into our inverse function. We'll get 6 minus 5 is 1. 3 minus 5 is negative 2. And 11 minus 5 is 6. Now, the purpose of this, even though it was nice and quick, is to, again, recognize that we had a list of inputs over here on our original function. Okay, that gave us some outputs, f. And then if we plugged those outputs back into our inverse, notice how 6 became the input for our next value, 3 became the input for our next, and 11 became the input for our inverse. Okay, that brings us back to those original values of 1, negative 2, and positive 6. Right? Inverses just undo our original function. So we're going to start kind of exploring what that looks like graphically as well. So for each of these problems, I want us to graph the original, find the inverse, then graph the inverse. So keep an eye out for a line of reflection so we can see what this looks like. If you graph this one in Desmos, okay, we have this equation here, f of x equals x plus 3. And if we were to go through and find the inverse, all right, we would find out that our inverse is x minus 3 if we actually worked through those steps. We could see that if I then graph this, f of x equals, it does not take our inverse sign, so we just want to leave it as f of x here, equals x minus 3. We'll see that, these lines look pretty similar, but they're kind of spaced apart. And if you were to go through and complete this exercise, you would notice that we actually have a line of symmetry here that happens across this black line that I'm creating, where the original function gets flipped over that blue function there. All right, let's see how that plays out in, let's say, this third example, okay? Wx equals 3x plus 1, our inverse, if you were to work that through, which I don't expect you to, you should be trying to do this on your own as well. This would be x minus 1 over 3. And if we graphed that, so 3x plus 1, x minus 1, and this is divided by 3, you'll notice that there is a reflection over this y equals x line, over this line of symmetry here that runs diagonal. So after you've explored, let's take this into notes and just kind of explore how inverses show up a few different ways. We have a table here with our original function. X gives us the output f, negative 3 gives us 2, 0 gives us 1, 5 gives us negative 4. Okay, if we were to build a table of the inverse values and use those outputs, 2, 1, negative 4, just like you saw in that first activity, we would just get our inputs of the original function all over again. So we'd get negative 3, 0, and 5. Those x and y values just flip around. Okay, in example 2, same thing happens. We're inputting 0, we get negative 1. So if we plug negative 1 into our inverse, we would get 0. We plug -8 into our original, we get 5. So if we take that 5, that output, put it into our inverse, we'd get -8. And the last one is just 12 and 12. So, like we saw in our little exploration of graphs as well, the graphs of inverse functions will be reflected across the line y equals x. So this red line here is the line of reflection that our inverses will show up across. Let's see how this shows up in a few examples. So in example 3, 4, and 5, first thing I'm going to draw in is that line of reflection to kind of help me make my sketch, right? We're reflecting across that diagonal. And if we do that, then I can kind of roughly trace what our inverse would look like. Our inverse would reflect off and look like this. Okay. Now, if we go to example 4, we'll draw that diagonal line here. Okay, this one's a little trickier to draw, but we can try our best. We're going to reflect across that diagonal line y equals x. And we'll kind of get a sideways parabola shape there. And that last function is actually our square root function. If I reflect across my y equals x line, we'll kind of still start at the origin and just kind of bend up a little bit in one direction. So the other thing we want to do today is kind of build our understanding of inverses and find some more complex inverse functions. The first case that we're going to explore is finding the inverse of a square root function. There's not too much complicated with this other than applying that idea of undoing a square root by squaring, just like we did when we were solving square root equations or solving radical equations. So in example 6, we're going to kind of go through the same process we went through yesterday, finding our inverse functions. We're going to swap out that g of x with y, so y equals the square root of x plus 5. Then that key step there where we switch x and y around, that's kind of the mechanic to setting up our inverse equation. So now it's x equals the square root of y plus 5. And then in order to undo this square root, we are going to square both sides of our equation. So in this case, we get x squared equals the square root of y plus 5 squared. And that just means that x squared equals y plus 5 because that square function, or that action of squaring, undoes that square root. Okay, we can subtract 5 from both sides here. Subtract 5. We'll get x squared minus 5 equals y. And I'm just going to write this to the right here because I'm running out of space. I'll clear my screen in a second. That means our inverse function g, the inverse of g, is equal to x squared minus 5. So not too much more complicated. Just got to remember that we undo that square root by squaring both sides of the equation. Let's see how this shows up in example 7. Just a little more complicated because we have this 2 out in front of it that we need to divide away first. So first thing I'm going to do is kind of set up y equals 2 times the square root of x minus 1. Then we want to do that swap, right? X and y get switched around. So x equals 2 square root of y minus 1. And we can divide 2 on both sides here. So we get x over 2 equals the square root of y minus 1. And now we're going to square both sides. And this can get a little tricky on the left. So on the right side, it just cancels out our square root sign, right? We're left with y minus 1. But on the left side, that exponent gets distributed and hits both of those terms. So we get x squared over 4. And then we'll need to finish this off by adding 1 to both sides of our equation. Let me move this kind of over to my left here so I have some open space. We then get x squared divided by 4 plus 1 equals y. which tells us that our inverse here is x squared over 4 plus 1. Now, the second more complicated equation that we need to kind of run into is our inverse of square functions. So if we're squaring something, we can undo that by taking the square root. However, we're going to need to make sure we take the plus minus version of, and we'll see that in a second here. So if we work through this, example 8, we're going to swap out our y equals x squared plus 1, and we do that second switch, x equals y squared plus 1. We can move our 1 over just like we normally would. We get x minus 1 equals y squared, sorry. Now to undo a square, we can take the square root of both sides. So we take the square root of x minus 1. We take the square root of y squared. And that will just leave us with y on the right. And we're left with the square root of x minus 1 on the left. Now, the thing that we need to do is we need to throw a plus minus sign in front of this square root. And here's why. If we look at our Desmos graph here, and let's go ahead and graph this, f of x equals x squared plus 1. Okay, we get this purple graph up here. But if we go and graph our inverse, f of x equals the square root of x minus 1, let me turn that into a red here. Notice how this red graph only takes up half of the function, right? It doesn't actually come down all the way to the right. So if we were to call that a negative square root, okay, that's where we get the lower half, but we don't quite get the upper half. And if you think about it, when you square a number, if you take 2 squared, you'll get 4. But you also get 4 if you take negative 2 squared. So when we undo the inverse there, and we undo that square action by taking the square root, we also need to make sure that we are doing the plus minus version of it. So if I draw this over, then our final answer is the inverse of x equals plus or minus the square root of x minus 1. So let's see that in one more example, example 9. Go through our normal steps. We get y equals 2x squared minus 3. Then we can swap these around. X equals 2y squared minus 3. We can add 3 to both sides. Get x plus 3 equals 2y squared. And then we would need to divide out 2 from both sides to get y squared by itself. X plus 3 over 2 equals y squared. And here's where we can take the square root. So I'm going to slide this over. You should have some space below on your notes here. I'm going to take x plus 3 over 2 equals y squared. And I'm going to take the square root of both sides. Okay, what that gives me is these, and we're going to want to make sure we take the plus or minus the square root of x plus 3 over 2 equals y. And so that means our inverse function h of x equals plus or minus the square root of x plus 3 over